We're going to Skype in with Dane, who is an Australia Telescope Australia Telescope Compact Array, which is run by Australian Telescope National Facility, a lot of ATNF. So ATNF run ASCA, run by ATNF. ATNF is part of CSIRO, which is Australian Science Engineer Institute, government organization that supports research and technology. And ATNF is headquartered in Epping, and they run few radio telescopes in Australia, one of them being PART, the big 64 dish. They transmitted first landing on the moon, as you know it, probably. And of course, compact array, which is array of 6 dishes. I mentioned this briefly when we were doing the telescope lecture. So it used to be just a west-east array, so the telescope could only move in one track. But then since 1998, they installed northwest track as well. The telescope can have a more configuration. It means it can get a fine-tuned resolution to whatever it needed for the source. So Australia Telescope Compact Array has duty astronomers, which are basically students and staff of ATNF who use telescope on a regular basis and are knowledgeable enough to support new observers. And so basically you will go for 7 days and you'll be on call for 24 hours if anything goes wrong. And you will train new observers, and you will also train them how to use the telescope, and you train them how to reduce the data. It's the only service like that in any observatory I've ever been. That's a complete package. They teach you how to use the telescope and they teach you how to reduce the data. Because what's the point of going and getting the telescope data and then you're stuck with them, you don't know how to reduce them? You really need experts sometimes to help you. Some data are easy to reduce, most of them are getting more and more complicated. So ATNF is really good in that respect, that it sort of provides the whole package. And so Dane is there at the moment because he's our student, but he also has a co-supervisor from ATNF. And he's going to give us a little bit of tour of the control room. So you have, being a radio telescope, you have control room. Telescope is sort of outside of your control room. But there's a lot of things that you have to keep an eye on. And also, he's able to get one of the observers. Hello.
Hello.
All right. We are on.
Awesome. Hey everyone. Hello.
All right, that good?
Let's say something.
Alright. That's better.
All right.
Hi.
All right. So you can start with your introduction.
Alright. So I'm in the control room for the Australia Telescope Compact Array. That's 6 dishes of radio telescopes that work together to look at some things in the sky. The people that run this, they have other telescopes in Australia. One of the ones is a very famous dish, and the difference between that one and this place here is that we have 6 dishes, and they're a little bit smaller, and they all work together to form different images and different information about what's in the sky. Right now, it's undergoing some maintenance, so there's no observations right this very second, but we'll talk about that later on. Each dish is worth $10 million, so it's worth doing maintenance to make sure everything's working correctly. So I'll see if I can show you a couple of dishes just out the window, because the way they're set up, there's 5 of them on a 3-kilometre train track, spread them out at different points, and there's a 6th one that's further 3 kilometres away. So you don't need to be actually inside the dish or anything. We have a control room here where we can have a look at all the parameters, and we can have a look at what's observing and all the conditions inside the telescope and make sure it's doing the right thing. So first of all, you can see over there, there's 2 of the dishes. There's not 4 that we can't see, but the 2 you can see outside the window, and they're both 22 meters across in diameter, just to give you an idea of scale. There's 6 in total, that's 2 of them. I'm going to show you some of the computers now to understand what you can see. So I'll start from over here. So hi to Jim.
Hi, Jim.
Hello, Jim.
Hi, Jim. We lost you.
Jim.
That's Jim Jackson from Boston University. They've been observing last, but we've frozen up. It's alright, so it's coming back. So the problem with ATNF, it has to be radio silent side, because otherwise it causes interference in your radio signal. So there's no Wi-Fi, there's only high internet, so he can't go around the dishes and show you the dishes, and you can't have a mobile phone, or if you do, you just zap your observations completely. Hello?
Come on, there
are
we
we
go.
back?
Yeah, so I think I heard Jasmina saying that you can't have phones or wireless, and the reason, so I'm currently plugged into an Ethernet cable, but it's not very stable because it falls out sometimes, so my apologies. So basically, we'll try that again. These computers over here. All good? Yeah. So it tells us about the temperature inside the telescope, if anything's going wrong. It's got some weather radars, some rain. It's also got some lightning radar. It's telling us about the cryogenics, and then it gives us alarms if things are going correctly. It also measures the wind speed, and it's too windy, we can't use the telescopes. It also tells us a little bit about whether they're pointing in the right direction, if we're actually where we think they're looking. So those are those three computers over here. And if we go to these three, this tells us all about the observing. So whether we are moving or whether we're pointing on the correct source, amount of flux that we're getting, if it's all in time, and if anything's, well, I suppose if all the systems doing what it should be. So these are the screens where we see the signals being detected, and from that we can understand if it's doing what we believe it should be, or something's definitely going wrong with what we're pointing at. So one other thing that really got me, if someone told me when I started astronomy that you can look at the galaxy during the day, through cloud, in the rain, I would have told them, one, that they were crazy, and they were definitely wrong. And then if they told me that you're not allowed to use your mobile phone or your microwave for dinner because that'll ruin your observations, I would have told them that they were even more crazy. But, welcome to radio astronomy. Radio waves, the cloud and the atmosphere doesn't affect it, they can go through it. And so this telescope is actually operational 24 hours a day. Because all during the day, all during the night, and then it only shuts down for maintenance if things go wrong. Which for me was quite puzzling. And
for the high wind?
Yeah, high wind as well. So if it's too windy, the telescope wants to point in the direction, but the wind's trying to shake it off, and it can actually be dangerous to the telescope, and if it wobbles too much, it's going to be pretty rubbish. So those are the only reasons that this shuts down. But all through the day, all through the night, and then so that's where I'm at the moment. Jasmina, would you like to get one of the observers on the Skype?
Yeah, that'd be great.
Alright, so I'll introduce him. His name is Jim. He's from Boston, as far as I remember. He had some observations a couple of days ago, and he's here to talk about the sort of stuff he was looking at.
Hi, everybody.
Hello.
Can you hear me?
Yes.
Yeah.
I apologize that I talk a little funny. But I can speak Australian, so if you ask me questions, I'll understand you.
So we heard that your observing proposal is about two very massive stars.
Yes?
And that you got very excited about the results you were getting.
Both things are true. So what I study is baby stars, how stars are born. So, stars are born all the time in our home galaxy, the Milky Way. The sun was born about 4 billion years ago, but I think the sun is a rather ordinary star. We like it, it's home, but it's not a particularly interesting star to me, because it's not particularly bright, it's not particularly massive. So the stars that I'm interested in are really massive ones. And a really massive star is much, much brighter than the sun, millions of times brighter than the sun. And it's about, maybe 100 times more massive than the sun. Now, what we don't understand is how these things can form. So the way a star forms is you have a ball of gas floating out there in space, and the gravity pulls it together. And when it gets hot enough in the middle, the star will ignite, it will ignite nuclear reactions, and then the star will shine. So I'm interested in what happens before the star is actually shining, and how these gas clouds condense and form little lumps, actually acid lumps. And what we found using this telescope last year, we were looking at a place where we think these big stars are forming, and we found two of the most massive stars forming in our Milky Way. They're about 50 and 80 times more massive than the Sun, and they were right next to each other on the sky. And what was really odd is that the bigger one seems to be in a younger state, a colder state than the smaller one. And that's very puzzling, because we think that the big stars go really fast, and the smaller stars take a lot of their time. So we were looking at these guys just a couple nights ago, and what we were detecting were molecules in space. So we were actually looking at things like water and methanol, which is wood alcohol, and we were looking at ammonia. Now, ammonia to you might be a wonderful cleaning solvent, but for us, it's a thermometer. We can use the signals from ammonia to tell how hot these guys are. And we were trying to find out which star of our two massive stars is warmer. And what we saw the ammonia signals coming in, we saw that both of them are very hot. So we're still very puzzled. But it's very exciting, because puzzles are good things in science. If you just found out what you were expecting to find, that's not particularly interesting. So now we have a puzzle to solve. How is it that we have these two very high mass stars forming, and the bigger star seems to be in a more evolved state than the younger star? So that was really dull.
No, that was very interesting. Any questions?
Yeah, why don't you ask some questions? No questions? Oh, come on.
Sorry, what? In what region of galaxy are these two stars?
So these are in the constellation Scorpio, in the galactic plane. So if you look at the Milky Way, have any of you seen Scorpius?
Yes.
It looks like a beautiful, it really is the one constellation that looks like what it's supposed to, isn't it? I mean, I don't see dogs or bears or rabbits in space. I see, but the Scorpion looks pretty good. So that's in the plane of the galaxy, and these stars were about 20,000 light years away, which is a good way across the galaxy, but not all the way across the galaxy. So it's about halfway between us and the center of the galaxy. And these stars form in the spiral arms. If you see a beautiful galaxy with the spiral arms are lit up by the big stars that form them. And so that's where we have to look to find our baby stars in the galaxy's spiral arms. And you can't see these things with an optical telescope. There's so much dust in these clouds that these clouds are absolutely opaque, and you can't see them with optical telescopes. You can barely see them with infrared telescopes. But as Dane said, the radio waves go right through this dust and can reach us here on the Earth.
So as far as we do in this course, we explain to students that the star exists because of the balance of radiation pressure that comes from the nuclear...
dance in Australia, that's amazing.
Comes from nuclear reactions and with the gravitational forces that pull things down. And the problem with these massive stars that are bigger than 10 solar masses is that radiation pressure becomes too big. And I'm the lecturer. Sorry, I'm the lecturer.
Yeah, that's impressive. That's theory.
So the problem is, of course, once they become 8 to 10 solar masses as they form, the radiation pressure becomes too strong and pushes away the rest of the material. So the big puzzle is how then this material gets accumulated. Does your research or your observations also try to answer some of those questions?
Absolutely. So this is the big puzzle with how these big stars form. They shouldn't form at all. The theory says that the light pressure should push any gases trying to fall down on the star away. So we're trying to understand that, and yes, our observations are working on that. So there are a couple ideas that are out there that we're hoping to test. So one idea is that as the star forms, it forms a disk around the star. And that disk is what planets are made out of. So the sun had one of these disks a long time ago, and planets condensed out. So the big stars will have these disks too. And the disks have all the dust in them, so the light can't actually go inside them. They're opaque, and the radiation pressure can't push the disk away. So maybe the material comes in through the disk. So that's one idea. If that's true, we should see disks. And we need a telescope like this with really good angular resolution to be able to see fine detail. Maybe we can see these disks. So we just took the data a couple nights ago, so when we process it, we're going to be looking for those disks. So that's going to be a test of this idea.
Well, that's, yep.
You're having trouble just trying to figure out the explanation between the two different stars you saw. What is your preliminary explanation for the difference?
I have no explanation. It's baffling. So the couple ideas we do have. One idea is that the stars didn't form at the same time. So if one star formed after the other, it could be in a less evolved state and still be bigger. But that's kind of stuff too. That would suggest multiple epochs of star formation in the same clump of gas, and that's speculative. So that's best guess what's going on.
Any other questions? Well, let's thank Jim Jackson from Boston. Thank you very much.
My pleasure.
And thank you, Dane. Thank you so much. That was awesome. Yeah?
Good.
All right.
Anything else you want to know? Or?
No, that's all we need to know. We'll see you here next week.
Good.
All right. Bye.